Hello everyone. Let us now talk about the Goertzel and Chirp transform algorithms. Let us look at some of the applications where the requirement of these algorithms you will clearly see. In some applications, you require only a few DFT frequencies, and one application is the frequency shift keying demodulation, in which two frequencies will be used to represent 0 or 1, meaning by 0 will be represented by one frequency and 1 will be represented by the other frequency. Now at the receiver side, you have to demodulate the bit stream, which is coming in the form of frequencies. Now you require a system so that you should be able to demodulate these two particular frequencies only, rather than using DFT and to come to know about each and every sample of the each and every frequency sample. All right, so you require an application where a selected number of DFT frequencies can be observed. Another example is the DTMF dialing system. Let me show you the diagram of the DTMF dialing system. Here DTMF means dual tone multiple frequency. This is the normal keypad of your telephone system, where the keys are present in the form of a matrix. Now this is 1, 2, 3, and the first row corresponds to a frequency of 697 hertz, second row 770, third row 852, fourth row 941. In the same way, the columns are also represented by one particular frequency. First column is 1209, 1336 for the second column, 1477 hertz for the third, and 1633 hertz for the fourth columns. So this forms the high frequency group and this forms the lower frequency group. Now when, let's say, 2 is pressed, so what frequencies will be transmitted? 697 and 1336. So once the observer at the receiver side observes that these two frequencies are coming, so he will be able to understand that 2 was pressed. So when 8 is pressed, the frequencies transmitted will be 852 and 1336. Again, he will come to know that 8 was pressed. So the problem at hand is to demodulate or to detect certain frequencies, not all the frequencies. So therefore, the Goertzel algorithm will be used in that context. Now, Goertzel algorithm reduces the number of real valued multiplications by almost a factor of 2 relative to the direct implementation by DFT equation. Thus, Goertzel algorithm is useful for computing a free frequency values. If many or more values are needed, the standard FFT algorithms, which include the frequency in decimation in time and the decimation in frequency FFT algorithms, can be used. All right. Now, Goertzel algorithm can be derived by converting the DFT equation into an equivalent form as a convolution, which can be easily implemented using a digital filter. Let us see how the derivation or how the system is developed for the Goertzel algorithm. Okay. Now this is the normal discrete Fourier transform equation. These two equations represent the DFT pair. Now, baseline for computational complexity, each DFT coefficient, if you want to calculate each coefficient or using this equation, then this requires n complex multiplications and n minus 1 complex additions. Now, for all n DFT coefficients, n square complex multiplications are required and n into n minus 1 complex additions are required. And if you want to observe the real operations for the complexity in terms of the real operations, then you can see that 4n square will be real multiplications and 2n into n minus 1 real additions will be used for the calculation of all the DFT points, right? And the twiddle factor is e to the power minus j to pi by capital N. So twiddle factor observes conjugate symmetry, and it also has periodicity in n and k, in both n and k. So Goertzel algorithm also makes use of the periodicity property. Now this is the periodicity property. What we have to do is that W subscript capital N minus nk when n is equal to capital N, so this takes this form. Now this is equal to 1. We know that it is quite obvious because W subscript n is e to the power minus j to pi minus j to pi by capital N. So when we put minus sign here, it becomes positive, and we put small n equal to capital N. So this k will be there, and in that case this equation takes the form of e to the power j to pi k equal to 1. Now if we use this factor and multiply this factor in the multiply the DFT equation with this factor, because this is 1 ultimately, so this factor is put here and this is my DFT equation. Now if I solve the DFT equation further, xr, and I, instead of n, I use an index r. So r equal to 0, xr e to the power, I take j common from because in both the terms j is common. 2 pi by capital N also I take common, and then k capital N minus r you will get in the exponent. Now I define one term which is ykn. Now what is this equation? This equation is these are the frequency samples. This is the DFT equation only. But only thing I have done is I have just put a factor which is actually 1 into this equation, and just I try to modify the equation. Now I define a term which is ykn equal to xr e to the power j 2 pi by capital N k n minus r multiplied by the unit step function un minus r. Now I define certain output which is yk, right? Now this is using xn equal to 0 for n less than 0 and n greater than capital N minus 1. Basically it is telling me about because this unit step function is also present in this equation, which I have defined it by myself. I have defined ykn like this. This factor is multiplied by the unit step function. Once it is multiplied by the unit step function, so this will be xn is equal to 0 for n less than 0 and n greater than capital N minus 1. Now xk is equal to now what is this? When I change the limits of sigma from 0 to capital N minus 1, what happens is this term reduces to because un minus un, this unit step function will be 1 from 0 to capital N minus 1 only. So it becomes basically equal to xk. Right. So what I want to say is that xk becomes ykn, and when n small n, I have put it equal to capital N, because in xk, if you look here, it is capital N. There is no small n term here in xk. Only thing is that small n is replaced with capital N. But I defined ykn with this equation. If I say that if n is equal to capital N, then my ykn, which I have defined here, becomes equal to xk, right? Now xk can be viewed as the output of a filter. Now ykn can be said to be an output of a filter, right? Of what filter? In which xn, if I use now instead of r, I use xn as a general usage of this index for time samples. Now xk can be viewed as the output of a filter to the input xn, and the impulse response of the filter hn equal to that means the xk will be the basically the convolution of this input xn and the impulse response of the filter hn equal to e to the power j 2 pi by capital N k small n un. So this is my impulse response of the filter, and xn is the input. Once I pass this input through this filter, then which is ykn, when small n is equal to capital N, right? That is also impulse response of the filter now is this, but while equating the output to equal to the xk, I will have to put small n equal to capital N. So this is the impulse response of the filter. Xk is the output of the filter at time n is equal to capital N. So let me summarize once again. What I have done is that in the standard DFT equation, I have multiplied this term, which is actually 1. So when I multiply this term with in the standard DFT equation, so I just modify the equation by taking j common from the exponents, and I get this value. Now I define one term ykn, which I say is the output of a system. Now what is that system? That system is basically performing the convolution of the input sequence xr or xn with a filter, with the impulse response of a filter, whose impulse response hn is given by e to the power j 2 pi by capital N kn into un. So this is the impulse response of the filter. This input xn is applied to this impulse response. Both will be convolved, and we get an output which is ykn. Now when ykn is calculated at small n equal to capital N, then we get xk as the output of the whole system, right? So that's what our Goertzel filter will be. This is the impulse response of the filter required, e to the power j 2 pi by capital N kn into un. So if I replace this with the twiddle factor, it becomes wn to the power minus kn un. Now if I take the z transform of this, because w subscript n, this will be a kind of alpha to the power n. W subscript n raised to the power minus k will be alpha to the power n un. So what is its z transform? Its z transform will be given by 1 over 1 minus wn to the power minus k z to the power minus 1. And if I, from this transfer function, if I obtain the difference equation, so I get, because hkz will become yz by xz. So if I cross multiply and take the inverse z transform, I will get ykn is equal to ykn minus 1 wn minus k plus xn. And if I represent this difference equation in the form of a structure, I will say that this is the xn, this is the output of the filter, and when the output of the filter is delayed by 1 unit of time and multiplied with this coefficient, we get this transfer function basically. And we have already assumed the initial rest conditions, right? So xk is what? Xk is ykn. The ykn is coming from this filter, is ykn when small n is equal to capital N. So this is to be remembered, right? This is not a standard DFT equation where we are calculating all the samples. We are now having a system where xn will be applied to a filter with this transfer function, and when small n will be equal to capital N, we get the output of the filter. Output DFT samples for all values of k we can calculate. All right. Now all the intervening values. So we have to calculate ykn, n is equal to capital N, but all the intervening values of ykn, yk2, ykn capital minus yk capital N minus 1 must be computed in order to compute ykn is equal to xk. Therefore, the use of the system as a computational algorithm requires 4n real multiplications and 4n real additions in order to compute xk for a particular value of k. Thus, this procedure is slightly less efficient than the direct method. However, it avoids the computation or storage of the coefficients wn to the power nk, since these quantities are implicitly computed by the recursion implied by this. So this algorithm will actually apply the recursion, and these values need not to be stored in the storage system. So this is the if we write the DFT equation and we put term 1 here, and we can put instead of 1 this term w subscript capital N to the power minus capital N k, because this is 1 only. And if we modify this equation and start substituting the values of n, we will get this recurrence equation. So we need not to actually store these coefficients, but we will get from the recurrence equation once the input will start coming and we are getting the output. So in a recurrence way, we will get all the values. Now it is possible to retain this simplification. Well, so we have what we have achieved till now. We have made a system. We have made our system to be simpler in the sense that we have to apply an input sequence to a filter, and we get the output equal to the xk when the small n is equal to capital N. Now we can retain this simplification while reducing the number of multiplications by a factor of 2. Let us see that part also. And ultimately we will come to the second order Goertzel filter. So this is our first order Goertzel filter, which we have just derived, because if you remember, this is the transfer function of the first order filter. Now we replace Wn to with its value e to the power minus j2 pi by n, right? So we get 1 over 1 minus e to the power j, because the minus sign was there, so minus sign will become positive sign if two minus signs will be there. So it will be 1 minus e to the power j 2 pi by capital N k z to the power minus n minus 1. Now we multiply both numerator and the denominator with this factor e to the power 1 minus e to the power minus j2 pi by capital N k z to the power minus n. And when we multiply the two factors in the denominator, we get this equation, right? 1 minus 2 cos of 2 pi k by capital N z to the power minus 1 plus z to the power minus 2. And if we draw the if we draw the structure of for this filter, so this filter will have this structure, because if we cross multiply, if we write hkz as yz over xz, and if we cross multiply, we will get this difference equation. And using this difference equation, I can draw the structure for this second order Goertzel filter. And when I put n, small n is equal to capital N, then I get the value equal to xk, as we were doing in the case of first order filter. And then when small n is put equal to capital N, then we can change the value. We can substitute the values of k, and we can obtain capital X0, 1, 2, 3 up to capital N, right? Okay. Now complexity for one DFT coefficient in this case is that if xn is complex sequence, then for the poles 2n real multiplications are required and 4n real additions are required. For zeros need to be implemented only once, because since we need to bring the system to a state from which yk can be computed, the complex multiplication by this coefficient required to implement the zero of the system need not be performed at every iteration of the difference equation, but only after the capital Nth iteration. So that is the advantage that we will get. And we will for this zero, we will have to perform only 4 real multiplications and 4 real additions. So complexity for all DFT coefficients, each pole is used for 2 DFT coefficient, approximately n square real multiplication and 2n square real additions. Okay, now let us look at the final advantage. In the implementation of the Goertzel algorithm, the total number of computations is 2n real multiplication and 4n real additions for the poles and 4 real additions for 0. So therefore the overall multiplications become 2 into n plus 2, and whereas 4 into n plus 1 are the real additions, which is about half the number of real multiplications required with the direct method. So here is the advantage that will be obtained when you use Goertzel algorithm, and you have to when you have to calculate some lesser number of DFT coefficients rather than all the coefficients. Then we can use Goertzel algorithm, and it gives an advantage of half the number of real multiplications required with the direct method. Now let us look at one more algorithm, which is the Chirp transform algorithm. The Chirp transform algorithm computes capital M samples of x e to the power j omega. This is the Fourier transform of the discrete sequence, right? So the Chirp transform algorithm computes M samples of the uniformly spaced samples of omega anywhere along the unit circle. Now once you get the Fourier transform of the discrete sequence, and you it will be represented by x e to the power j omega, and you take capital M samples uniformly spaced around the unit circle, and this the algorithm therefore computes x of e to the power j omega naught plus k delta. I will explain what is this omega naught and delta omega. This is given by n equal to 0 capital N minus 1 xn, which is the discrete sequence, and we take its Fourier transform. It becomes e to the power minus j omega naught plus k delta w. So that means we have put w omega k. Let me show you that omega k is equal to omega naught plus k delta omega, which we put here. We replace x e to the power j omega k. We replace omega k with omega 0 plus k delta w on both the sides. All right, where the starting frequency is omega naught and the frequency increment will be delta omega once we go around the unit circle. And now for the specific case of DFT, omega 0 will be equal to 0 and capital M is equal to n. All right, we take these many points around the unit circle, and delta omega, that is the step, the spacing between the two frequency points will be delta omega, and this is given by 2 pi divided by capital N, because 2 pi is the overall circle, and how many frequency points we will get is determined by 2 pi divided by capital N. The Fourier transform corresponding to this more general set of frequency samples, this is the Fourier transform, where omega k, as I have already explained, is omega naught plus k delta omega, and w, which is w is also defined by e to the power minus j. I have already defined delta omega. Delta omega is 2 pi by n, so w will be actually e to the power minus j divided by minus j 2 pi divided by capital N. So which is the okay. Now let us again look at the DFT formula. This is e to the, that means we are taking the Fourier transform, e to the power x of e to the power j omega k equal to n going from 0 to capital N minus 1 sigma xn e to the power minus j omega k n, where k varies from 0 to capital N minus 1. Now where omega k I have already defined, which is omega 0 plus k delta omega. Now defining w equal to the e to the power minus j delta omega, this becomes we put this omega k equal to omega 0 plus k delta w delta omega in this equation, and we also put e to the power minus j delta omega equal to w. So this comes out to be this factor, and of course it has to be multiplied with xn. Now what I do is that I did some some manipulation into this exponent, where I say e to the power minus j omega naught n, same as it is coming, and I take w n square by 2, right? I multiply it with w n square by 2, w k square by 2, and I also multiply with w of minus k minus n whole square by 2. So ultimately we will get back this equation only. Now if you look at this equation, so and if you take w n square by 2 common out of this, you will see that this is this is e to the power minus j omega naught and w n square by 2 xn convolution with w minus n square by 2. So these two will be convolved with each other. Now by defining, if we define this factor e to the power minus j omega naught n w n square by 2 of xn, if we define it with a new sequence which is gn, the above equation is equivalently represented as wn square by 2 gn into gn convolution with w minus n square by 2. Now e to the power j omega k is the convolution of the sequence gn and w minus n square by 2 followed by multiplication with this factor. All right, the sequence w minus n square by 2 can be thought of as a complex exponential sequence with linearly increasing end frequency n delta w. Now in radar systems, such signals are called chirp signals, and therefore the name of this transform is chirp transform, right? So we have a convolution of the two sequences Gn and W minus n square by 2. And the sequence, if it is assumed to be a complex exponential sequence, the sequence can be thought of as a complex exponential sequence with linearly increasing frequency. So this is how the frequency is increasing if we go around the circle. And in the radar system, such signals are called chirp signals. Now, this can also be represented in the form of a block diagram. So if you see, this is the input sequence xn, and this is e to the power, because in the equation, if you see, this, what is this gn? Gn is e to the power minus j omega naught n omega w n square by 2, right? It has to be multiplied with xn. So that's what is done here. This is multiplied with xn. So this becomes gn sequence. Now this is applied to uh, w minus n square by 2 as an input. Now this will here the convolution will take place, and finally this output needs to be multiplied with wn square by 2, and we get final x of e to the power j omega naught. So this is the block diagram of a Chirp transform algorithm, which can be used to calculate the DFT uh, frequency points. Okay, thank you.